everybody. This is Mrs. Wild from Wisconsin Connections Academy Physics A, and we are going to be looking at momentum still in this lesson, but we're looking at elastic and inelastic collisions. And I mean, it kind of relates back to that law of conservation of energy that we had in just one of the recent lessons that we were looking at. So your keywords here are collision, elastic collision, inelastic collision, law of conservation of energy, and the law of conservation of momentum. All right, so again, with momentum, we look at specifically collisions, right? Because it's an interaction between two objects. And something doesn't have momentum unless they have both mass and velocity. So they have to be moving, essentially, right? We can look at examples of collisions and what happens during the collisions because different things happen depending on the type of collision and what is colliding. So not only does it have to do with the mass and the velocities of the collisions, but the materials of the objects that are colliding does affect that's what happens in the event of a collision. An elastic collision is a collision that conserves both kinetic energy and momentum. Now, what's kind of confusing, I think, is that when you think of an elastic collision, you sometimes think of something being stretchy like an elastic band. But unlike that, I want you to think of what's happening in the collision because elastic is referring to the collision itself. If you think about an elastic rubber band, for example, if you stretch it, it then, when you let go, it returns to the same shape. So that's kind of the idea behind elastic collision. Everything is conserved, both kinetic energy and momentum. Now, we really haven't talked a lot about kinetic energy. I assume you had some information on kinetic energy when you took physical science years ago. So we are going to be revisiting kinetic energy, even though we haven't really visited it yet, but it kind of gives you an idea of what's happening. Now, the difference between momentum and kinetic energy is that momentum's formula is mass times velocity, and the formula for kinetic energy is 1/2 mass velocity squared. So you can see that it uses the same variables in it. It's just that there's a difference in the actual equation. Inelastic collisions will conserve momentum, but not kinetic energy. It does give you an example. For example, if you take two marbles that are made of glass and you roll them and they hit each other, they would be, let's say you have them, I don't know, going in opposite directions towards each other. Those are some really bumpy marbles, but pretend they're really circular. Okay? Once they strike and they hit each other in the middle, see if I don't think I can move it. Nah. They're going to hit and bounce backwards in the opposite direction. So the direction will change, but the speed and the mass doesn't change either. But the speed or the velocity of the marbles is not going to change, right? It will be opposite what it was because remember velocity is a vector, but overall it will be conserved. When we look at inelastic collisions, an example would be if I take a marble and collide it with a ball of clay. So here I'm taking a marble, better circle, and it's rolling into this amorphous ball of clay. Once it hits the clay isn't going to really, it might move a little bit, but the clay itself is going to deform, right? So the marble will be intact, but the clay is just going to deform around the marble. So momentum is going to be conserved because some of the momentum of the marble will be passed to the clay. The first marble will likely slow down and the clay will move in this direction backwards a little bit too. So you have to add the momentum of the marble to the momentum of the clay, but the energy is going to be used to deform the shape of the clay. So we're actually using that energy to do work. You're going to learn later that energy is actually defined as the ability to do work. So it's actually doing work on the clay itself. okay? So that's your other type of collision. So you might even like get in your head mixed up because, oh, clay is kind of elasticy. But no, don't use that. Remember that elastic means that it goes the same, everything's the same kind of before and after. It goes back to what it was before. So velocity is maintained in an elastic collision. In an inelastic collision, it's not. All right, so no collisions are truly inelastic. Remember that in physics class, we oftentimes come up with these ideals, which helps us to better kind of do the math and understand what's going on. Same as there's no true closed system, there's no really true 100% elastic collisions. There's usually some degree of inelasticity. So you might see that the momentum after isn't exactly the same. When we use things that kind of try to limit those external forces or are extremely hard and things like marbles, for the most part, we can usually model the elastic collisions as being close to the same. In a physics classroom, we'll often use these things called air tracks. And if you have ever played air hockey before, it's similar to that, where we have these little tracks that cars run on, and there's like air underneath of them. So the cars themselves, there's no friction between the surface, or there's very limited friction between the surface and the car, and therefore we're able to see better that conservation of momentum. But I don't have one of those. I wish I did. It would be kind of cool, but I don't. And you can do it on ice too. That's another way to kind of reduce the friction so you can really see that conservation of momentum as well. So remember with elastic collisions, energy is conserved as well. So we're talking about kinetic energy. Kinetic energy is written as 1/2 mass times velocity squared. They wrote it as 1 mass velocity squared over 2. Mathematically, that is exactly the same thing. Um, I've always written it like this. You certainly could also write it like this, mv squared over 2. That 1 on top is unnecessary. It's just a placeholder, right? But you'll hear me talk about 1/2 mass velocity squared more frequently because that's just one that is, I don't know, like more commonly used, I think. So you can write the collision, you can write the kinetic energy before and after, very much like we did it with momentum earlier. You actually have the object 1, right, plus object two's kinetic energy. This is initial before the collision, would give you the kinetic energy of the objects after the collision. So it's actually kind of big. They're giving us a slider here to show that, but okay. So again, this is before the collision. This is before the collision. This is for object 1, and this one is for object 2. When you add that together, it equals the kinetic energy after the collision. Please keep in mind that whenever we're using vectors, you have to pay attention to directionality. If these arrows had changed their direction, then the velocity would be opposite in sign, right? So for some reason they hit each other and bounce back the opposite direction, make sure you make their velocities negative from what they were to begin with, because that's very important. If we have two objects moving towards each other, two marbles coming towards each other like this, the velocity, if let's say they have the exact same speed, right? Then the velocity of the first one is positive and our second one is negative because they're moving in opposite directions. Mass is never negative because mass is a scalar quantity. It doesn't have directionality, but velocity is, okay? So just make sure you do that because it makes a difference when you're trying to determine what the total momentum is. All right. And then they're talking about conservation of energy sample problems. And again, it's just very similar to what we did before. I can work through this one with you So we said in the diagram, and I'm going to actually split my screen right now just to give myself a little bit more writing space. But in the diagram, a 1 kilogram cart travels 2 meters per second to the right. So it's giving us the direction. So that's, I like to break this down to start with, you guys, and just do like, let's see if I can do this over here. Oh, nope, I have to use the pen on this page. So we have cart number 1. This is how I like to split it up, okay? Before, after, okay? Um, sorry. How do I add a line? Okay, I'm just gonna put a line in the middle. I thought I was gonna try to draw a line, but that wasn't happening. So we're just gonna put a line in there. Okay. So we have cart 1. Really? Said that was an R. Cart 1. Okay. There we go. I'm using my mouse, so just like bear with me when it comes to a penmanship. Okay. It has a mass is 1.0 kilograms. Its velocity is 2.0 meters per second. And for this particular problem, I'm just going to make that positive. So to the right in my problem here is going to be positive. How do you know if it's positive or negative? You really don't. Just make sure that um, you you observe the rules that you put in place. So if you're saying that to the right is positive, that means to the left is always negative, right? So you just have to observe the rules that you put in place. And let's see here. So I can do cart 2. Oh, I'll just put it over here. This is before, right? Okay. So then we have cart 2 is the mass is 0.75 kilograms. And the velocity is 0 because it says it's at rest, right? So we add them together. We say we want 1/2 mv squared for cart 1 plus 1/2 mv squared for cart 2. This is for cart 1 and this is for cart 2. We add them together and that gives us our total kinetic energy. I'm using a fancy term here, the sum of the kinetic energy, okay? So cart number 1, the mass is 1, so 1/2 of 1. So 1/2. So we'll just plug in the numbers here, guys, okay? There we go. Give me un momento, please. Here, I'm gonna have to do a little clicking and dragging here because I didn't give myself enough space. Okay. So 1, it's always important. I think it's important to write these things out, you guys, instead of trying to do it in your head because it might be easy right now to do it in your head, but later on it might not be as easy. And the velocity is 2 meters per second. Don't forget to observe those significant digits. Sorry, that was a really bad slash. And we're squaring that, right? So let's see. 1/2 mv squared. Oh, we have to divide everything by 2. Okay, divide it by 2. So 1 kilogram times 4 meters squared per second squared. 1/2 kilogram meter. Okay. Sorry, guys, my mouse is not being real cooperative here. Should get you up under you. I can't get it to go down where I want it to go. There we go. All right, 1/2. Oh, we lost our mass times velocity squared. Okay. So we have basically, add these together, it's 4 divided by 2, right? I'm just going to divide that out. So it's 2 meters squared per second squared. Oops, I lost it. Kilogram, sorry. All right, so a kilogram, this is another thing, guys, a kilogram per second squared. So this part here is the definition of a Newton, a kilogram meter per second squared. So our final answer is 2 Newton meters or 2 joules, okay? And joules is a unit of energy, so that's right. So then let's look at after the collision. So after the collision, what we're looking at here is cart number 1. So let's look at cart 1 after the collision. We know the mass does not change. It's not like it's getting smaller or anything. So that's still going to be 1.0 kilograms. The velocity, it says, it's still going in the same direction, but now it is now slowed down to 1.5 meters per second. Okay. And cart 2, it didn't change size either. It's still at 0.75 meters. Or sorry, 0.75 kilograms. My bad. But it doesn't give us the velocity. It says we don't know what the velocity is. That's what you're trying to solve here for, the velocity. Okay, so let's go back down. All right, so we know that the total amount of kinetic energy before the collision is 2 joules. Well, we know that energy is conserved because it's an elastic collision, and that's one of the things about elastic collisions, it has to be conserved, right? So what we need is we need to figure out the energy of cart 1, and then we need to figure out the velocity component of the energy of cart 2. So it's probably easier if we kind of break this down into steps in the solution. They're giving it to you as one whole giant equation. I'm going to break it down into steps, just make it a little bit easier to see. So let's get the kinetic energy of cart 1 first. So cart 1, let's see, cart 1. Let's look at 1/2 of 1, and then velocity squared is 1.5. We'll do that, we'll square that, okay? So 1.5 squared is 2.25, and then divide that by 2, because All right, so 2.25 divided by 2 is 1. So the kinetic energy of cart 1 is equal to 1.125. And we have to add the kinetic energy of cart 2, right? So going down, let's take 2 joules, which is the left side of the first problem, and we'll set it equal to 1.125 joules plus the kinetic energy of cart 2. We're just going to subtract that from both sides, okay? So 2 minus 1.125 is equal to 0.875. Is equal to, and now let's expand that to 1/2. The mass of cart 2 is 0.75. Oh, sorry, my mouse is being a real big pain in the butt today. And then times the velocity, which we don't know, squared, right? So let's figure out this part, guys. 1/2 of 0.75. Well, let's just do, yeah, 1/2 of 0.75. 0.375 v squared equals 0.875 joules. Divide both sides by 0.375. It's kind of a long problem. My writing's getting worse as we get to the bottom. So 0.875 divided by 0.375 is going to give us 2.33. So 2.33 equals v squared. Now we just have to take the square root of both sides. And square root of that is 1.5. I'm looking at my, looks like we are looking at 1.53 meters per second. All right, let's check and see what the solution was. Oh, they came up with 1.5. I think I missed the significant digits. We should only be to the 10th place, so that's my bad. All right, we'll just get rid of that. So I did it slightly differently, but otherwise pretty similarly. I just kind of broke it down into steps. But essentially, we just want to figure out that one unknown variable. So hopefully that looks somewhat familiar to you. And conservation of momentum works the same way. We did problems with conservation of momentum already, but instead of using the 1/2 mass times velocity squared, you're just using the m1v1. So again, m1v1 of cart 1 plus m2v2 of cart 2, right? So you're adding this is going to be before the collision, right? Before. And this part is going to be after the collision. That's the most important part. If you can remember that, then you're golden here. All right, so that looks to be kind of all you need to do for this particular lesson. If you have anything you have additional questions on, please feel free to reach out. If you want to do more practice problems with elastic and inelastic collisions together, let me know. Otherwise, I hope you have a great rest of your day, and I will see you guys in the next video.